Hi guys, welcome to the lesson of partial differential equations. So in previous class, we discussed about the solution of heat equation with the non-homogeneous directly boundary conditions. So now in this class, we are going to start Neumann boundary conditions, and we will talk about the homogeneous Neumann boundary conditions and non-homogeneous Neumann boundary conditions as well, right? So Neumann boundary conditions that we discussed in earlier classes, that these are the derivative boundary conditions. And if they are homogeneous boundary condition, it means that the first derivative at the boundaries is equals to 0, right? So at end A and at end B, right? So at both ends, the derivative boundary conditions are given, that is equals to 0, right? Here u of x, ux of l comma t is 0, ux of 0 comma t is 0, and the initial condition is ux of 0 is equals to some function of x, right? So again, we will use the method of separation of variable for these homogeneous boundary conditions. We will apply three cases. We know about the cases when we will separate the variables. We said that the variables are the ratios and they are equal to some constant, right? So, and then we also said that these both ratios are independently equal to the constant. Then after that, we will we know that now in this problem, the issue is that we don't know either lambda is 0, positive or negative. So we discuss all three cases, right? So in order to get all solutions, and then by using superposition principle, we can add up all solutions and we can generate a general solution for the heat equation, right? So here is the method of separation of variable. We assume that ux of t is equals to the product of function of x and function of t. Therefore, we differentiate it with respect to x, and then again with respect to x, and then with respect to t, because we know that in our heat equation we have ut is equals to c squared uxx. So we need to find this uxx and ut. All right, so now we can see that the variables are separated and they are transformed to a second order differential equations. One second order differential equation and one first order differential equation. So we can solve these differential equations uh, by using integration or by using auxiliary equations, right? So first of all, we will discuss the case when lambda is equals to 0. So when lambda is equals to 0, x double prime will be equals to 0, because we know that this is the original equation, x double prime x is equals to lambda. And when this lambda is equals to 0, so we're left with x double prime is equals to 0. We will integrate this twice, so we will get this solution c1x plus c2, right? And then for t prime respectively, what we did is we know that we have t prime over t is equals to 0. It means that we only left with t prime is equals to 0. When we will integrate this, we will have a constant only on the right hand side, right? So t is equals to c3. Now we are given with some boundary conditions that are derivative boundary conditions, right? So x prime of so what we will do, we will differentiate this x first, so we will get c1, and then we will apply the boundary conditions. So from here we get applying the boundary conditions. This is x prime is equals to c1, right? And again, if we apply the boundary condition of x prime of l, again we will get c1, right? So c1 is equals to 0 because the boundary conditions are 0, right? So c2 will be any arbitrary constant, so ux of t will be equals to now xt, that is our assumption initially, and then this will be equals to c2 times c3, because x is equals to c2, c1 is 0, and t is equals to c3, right? So their product can be written in this form. So this is T is equals to C3, right? And now these both are constants, so product of a constant can be written as another constant, right? So we can write C2, C3 is equals to A. So now in this case, u of xt is equals to A. Now you can see that this is a non-trivial solution. In previous cases for homogeneous Dirichlet boundary conditions, we solved for lambda is equals to 0 and we got a trivial solution. There was u of x comma t was equals to 0, right? But in this case, u of x comma t is equals to A. That means it's a non-trivial solution. So this is case 2 when lambda is greater than 0. So we will assume that lambda is equals to p square to make sure that it will remain positive always. And then again, we will apply same condition. We will write p square in place of lambda in both the equations. And then we will solve this differential equation using these auxiliary equations, right? And after solving this, we get the roots r is equals to negative positive p and m is equals to p square c square for this t, right? So we will construct the solution that will be x is equals to c4 times e to the power px plus c5 times negative e to the power px. And then t is equals to e to the power p square c square t, right? Now we will apply the boundary conditions on this equation. First of all, before applying the conditions, we will differentiate this equation because derivative boundary conditions are given, right? So when we will differentiate this, we will get pc4 times e to the power px negative pc5 times negative e to the power px. And now we will apply the boundary conditions. So boundary conditions are given as ux of 0 comma t is equals to 0, which actually means that x of 0 is equals to 0, right? Because this refers to x. And then ux of l comma t is equals to 0, which means that, sorry, there is x prime of l is equals to 0, right? So we'll apply the boundary conditions respectively, and when we will apply the conditions, we will get two equations, and we can solve these equations simultaneously. So after solving this simultaneously, what we will get is we'll get C4 and C5 is equals to 0 because both boundary conditions are equal to 0, right? So you're left with the solution u of xt is equals to 0. Now that is a trivial solution. So we don't need a trivial solution. It means that this solution is useless for us. Now we will talk about the case 3, that is lambda is equals to lambda is less than 0, right? So for lambda to be less than 0, we should use a negative constant. So we use negative p square, right? So it will be always negative. Whatever value we give to p, it will be negative always, right? So again, we have generated two differential equations. Again, we will solve these differential equations. By solving this equation, we get r square is equals to negative p square. It means that this is a complex root. So sine and cosine will be generated from this equation. And this m is equals to negative c square p square. It's simply a single root. So we can write the solution in this way. X is equals to a cos px plus b sine px, and t is equals to c e to the power negative p square c square t. Again, we need to apply the boundary conditions. So again, we will differentiate this x, right? Because we are given with derivative boundary conditions. So this will be ap sine px plus bp cos px, right? And then we will apply the boundary conditions. The conditions will be now x prime of 0 is equals to 0 and x prime of L is equals to 0, right? So we will apply the condition x prime of 0 is equals to 0. So negative AP times sine 0 plus BP times cos 0 This will make this function 0. So we're left with BP. So B is equals to 0 because P cannot be equals to 0, right? So B is equals to 0. Therefore, we will only left with the solution x is equals to a cosine px, right? This one. So now when we will differentiate this, we will get negative AP sine px. And this we know that negative AP sine px. For this, we have a boundary condition of x prime of L is equals to 0. So here we will apply x prime of L. So it will be negative AP times sine PL is equals to 0. So this AP will move to the right hand side and it will be 0. And we will get sine PL is equals to 0. So sine PL is equals to 0 means PL is equals to sine inverse 0. And from previous lessons, we know that sine inverse 0 is equals to n pi. We can write PL is equals to n pi. From here, we can get the value of P, that is n pi over L. Therefore, we will plug this value in the equation. Now we are only left with this form for x, right? Because we already showed that B is equals to 0. So this one, right? So what we did here is we replaced the value of P here and pi over L, right? So now the equation is u of xt is equals to AC cos n pi x over L times e to the power negative n pi c over L whole square t. All right, so now we got two solutions, two non-trivial solutions actually. That is, first solution was for lambda is equals to 0, and the second solution is for lambda is less than 0. And for lambda greater than 0, we got trivial solution, so we don't need that solution, right? So we'll use the principle of superposition. We will add both the solutions. So here for lambda is equals to 0 is the solution, and here it's for the lambda less than 0, right? So by superposition, we add both of these. So this is the general form of the solution, right? Now we will apply initial condition to get the particular solution, right? So let's say the initial condition is given as u of x comma 0 is equals to f of x. So u of x comma 0 is equals to a plus sigma n is equals to 1 into infinity a n cos n pi x over L. E to the power 0 will be 1. So this is equals to f of x. And we can see that it is a Fourier cosine series. So we can apply the half range Fourier cosine series to find f of x. And just to make it compatible with the Fourier series, we just assume that a is equals to a naught over 2, and a is a constant, so we can do that. It doesn't matter, right? So we can do that just to make compatible with the cosine Fourier series. Right now, there is a clearly a cosine Fourier series. So we can find a naught and a n, the coefficients of Fourier cosine series, by using the formula we know, right? A naught is equals to 2 over L integration 0 to L f of x dx, and a n is equals to 2 over L integral 0 to L f of x cosine n pi x over L, right? So in this way, and by substituting the values of a naught and a n in the general solution, we can find the particular solution. So we can solve the heat equation for the homogeneous boundary conditions, homogeneous Neumann boundary conditions in the similar manner. And now let's take an example. If initial condition is given, let's say that the initial condition is given ux comma 0 is equals to this piecewise function, right? So we are already aware of solving piecewise functions, generating their Fourier series. We talked about it in the previous lessons, right? So here a naught will be equals to piecewise integrals from 0 to L by 2 and from L by 2 to L, and we will integrate this. We will find a naught from here. This will be equals to L over 4 on simplification. So a naught is equals to L over 4, right? And similarly, we will get an by integrating uh, using the by part, because here we have two functions, x and cosine of this function, this angle, right? So here n is equals to, we already write that an is equals to 2 over L integral 0 to L f of x cosine and pi x over L dx, right? So we will use this integral to find the coefficient a n. So it will be 2 over L, and the integral of x cosine and pi x over L is so this function. Now we will apply the limits, and we can see that on applying the limits, we generated this form, that is an is equals to L over n pi sine n pi over 2 plus 2L over n square pi square cosine n pi over 2 minus 2L over n square pi square. So we got both a naught and an, so we can plug this in the equation, in the general equation. So this is a naught over 2. It means that if a naught is equals to L by 4, so a naught over 2 will be equals to L over 8. So we can write L over 8 in place of a naught over 2 right here. And then similarly, we'll write this a n here, and with cosine n pi x over L times e to the power negative n pi c whole squared times t, right? So this is the particular solution for the given initial value boundary value problem. And you can see that this is not a difficult task. It's simple. Just the difference between the homogeneous Neumann and Dirichlet boundary conditions is that in this type of boundary conditions, you can see that we have a non-trivial solution for lambda is equals to 0. But in the Dirichlet homogeneous boundary conditions, we have the non-trivial solution for both lambda is equals to 0 and lambda less than 0, right? So when now here we can see that if time t tends to infinity, we will get a constant temperature that is L by 8, right? Because if time t tends to infinity, this whole will become 0, right? This whole will become 0 when time t tends to infinity, and we will only left with this one, L over 8. So we will left with a constant temperature, right? So this is the particular solution. So in this manner, you can take some more problems. Like here it's problem 1 that is solved for the initial condition u of x comma 0 is equals to cosine x, and for the second condition you can solve for u of x comma 0 is equals to e to the power x. So you can solve the problem for your practice and make things easier for you in the exam, right? Now here is another problem, that is solution of one-dimensional homogeneous heat equation with non-homogeneous Neumann boundary condition. So now we will apply the non-homogeneous Neumann boundary condition, right? In previous example, we applied the homogeneous Neumann boundary conditions. Now we are dealing with the non-homogeneous Neumann boundary conditions. So non-homogeneous Neumann boundary conditions are showing that there is some temperature at both ends, and the conditions are the derivative boundary conditions, right? So there is some constant temperature at both ends, that is A and B, but their derivatives, that is du or dx at x is equals to 0 is equals to A, and du over dx at sorry, this is not 0 comma t, this is L comma t. Here it is L comma t, right? At x is equals to L is equals to B. So again, we will use the same approach of steady state and transient temperature, because now these are the non-homogeneous boundary conditions, right? So we will have two solutions, one is steady state and other transient temperature, right? So now we know that for the steady state and the transient temperature, the solution is given by ux of t, ux comma t is equals to wxt plus vx, not vxt, it's vx. All right, so we need to have a correction here, it's vx only. Therefore, steady state temperature means that the change of temperature with respect to time is zero, right? So we will left with this c squared dou square u or dou x square is equals to 0, which means that this is only a function of x, right? So it only depends on x. Now temperature only depends on x, so we can write it in this way: d square v over dx square is equals to 0. We will solve by integrating it twice. We can integrate this twice to get the solution, that is c1x plus c2. Now similarly, we will apply the boundary conditions. From condition 1, we can see that v prime of 0 is equals to a, v prime of L is equals to b, right? So we will apply the boundary conditions to find c1 and c2. So here we go. When v prime of 0 is equals to a, so it means that first of all v prime will be equals to c1, and it means that c1 is equals to a, right? So this is c1 is equals to a, and again when we will apply the v prime of L is equals to b, then what we get is c1 is equals to b. Now this is a contradiction, right? So c1 cannot take two values simultaneously. Therefore, this can only be true if a is equals to b. Otherwise, this is an inappropriate problem, right? It cannot happen, right? So it means that a should be equals to b in the boundary conditions. So the boundary conditions actually should be like this: ux of 0 comma t is equals to a, ux of L comma t is equals to a, right? So these should be the boundary conditions. Otherwise, this problem will be inappropriate. As we can see that C1 is taking two values, that is a contradiction. It cannot be happen, right? So now we will assume that A is equals to B, and that is true. If A is equals to B, we can follow the problem. We can continue, we can carry on. So V of X is equals to AX plus C2, right? So because Vx is equals to C1x plus C2, right? So we found C1, but we cannot find C2. So we can say that C2 is any arbitrary constant whose value is not affecting the problem. So we can say that this, we can assume this to be 0. So we will have Vx is equals to Ax. So this is correct, right? We don't need to be worried about this. We can assume that this is 0, so Vx is equals to Ax. And again, so Vx is equals to Ax. Now we can solve for the transient temperature. And remember that A is equals to B. And now we have to transform the problem, transform the boundary conditions, right? So we are given this Ux of 0 comma t. We found V prime of 0 comma t. This is V prime of L, right? So Uh, let me write it again. This is V prime of 0 and this is V prime of L, right? So here we can see that this ux 0 comma t minus V prime of 0, that is ux 0 comma t is given as A. This is ux 0 comma t, and ux 0 comma t. And again, we know that V prime of 0 is also equals to A, right? So A minus A will be 0, and again Wx of L comma t is equals to Ux L comma t minus V prime of L. Again, this is A minus A, so it will be 0, right? Then the boundary conditions will be equals to wx comma 0 will be equals to f of x, because u of this is actually u of x comma 0, and this negative vx we already found here, right? So we can write f of x minus ax. So now we know that the solution to above problem is given by wxt is equals to sigma n is equals to 1 an cosine n pi x over l e to the power negative n pi c over l squared t plus a naught over 2, right? In the form of a Fourier cosine series, because now this problem is homogeneous Neumann boundary condition, right? So we can apply the initial condition for this problem. Here is our initial condition, that is f of x minus ax. So we will apply here f of x minus ax, and we can say that let f of x minus ax is equals to gx, right? To make things easier and simpler, so now we can find a naught and an by these are the coefficients of Fourier cosine series, right? So we can find them easily by using the integration, right? And then substituting in the original equation, in this equation, we can say it equation number 2, right? In the equation number 2, and we will get this form: u of x comma t is equals to ax, because u of x comma t is equals to, we know that u of x comma t is equals to vx plus wx comma t, where vx is equals to ax and wx comma t is equals to this part, right? So in this manner we can get the solution for non-homogeneous Neumann boundary conditions, but we should remember one thing, that the non-homogeneity, that is we initially take ux 0 comma t is equals to a and ux l comma t is equals to b, but remember that a should be equals to b, right? Otherwise that will be inappropriate problem and we cannot solve that problem, right? So now we can take some initial condition and we can solve, we can generate a solution, and let's say that g of x is equals to ax is the initial condition. Remember, g of x is equals to f of x minus ax, right? So we are saying that g of x is equals to ax. It means that we are assuming that f of x is equals to 2ax, right? So whatever is given, you can find g of x. If g of x is given, it's fine as well. But if f of x is given in the problem, you can find g of x, right? By this that we uh, found initially, right? So now we are given with g of x is equal to ax. So we will calculate this coefficient of Fourier series a naught, which is equals to 2 over L integral 0 to L f of x dx. This will be AL, this will be cancelled with this 2 will be cancelled with this, we will only left with AL. Here it's A, right? And then we will calculate AN. So again, AN will be 2A over L times x cosine and pi x over L dx. We will integrate this using the by part rule and we will get this function. Then what we did, we applied the limits from 0 to L, and we are only left with this will be 0 because sine and pi, this will be 0 in both cases because sine 0 is also 0 and sine and pi is also 0. And this cos and pi will be negative 1 time, or negative 1 to the power n, and this cos 0 will be 1. So this will be the final form of an, right, after simplification. Now we can substitute this an and a naught into the equation. Here we go. This is al over 2 plus sigma, because we said that a naught is equals to uh, a naught over 2, right? So we found a naught as al, so it will be equals to al over 2. Sorry, not this. This is like this. All right, so this is al over 2, and this is sigma n is equals to 1 to infinity. This is an, and times the cosine n pi x over l times e to the power negative n pi c over l squared t. Now we can generate the particular solution by using the superposition principle. So we will add up steady state temperature and transient temperature. So this is the steady state temperature. We already found AX. And this is the transient state temperature, right? So this is the final answer for this problem, for this initial boundary value problem. And we can check this solution, either it's correct or not, by using the boundary conditions and the initial conditions, right? So here we checked g of x is ax. It means that f of x is equals to 2x, because g of x is equals to f of x minus ax, right? So here we want to verify the solution. The boundary conditions were given as 0 comma t is equals to a, and l comma t is equals to a also, because we said that a is equals to b. Therefore, ux comma 0 is equals to f of x is equals to 2ax. And because these are the derivative boundary conditions, so we will first find the derivative of the function. So it will be ux is equals to a minus sigma n is equals to 1 to infinity 2a l over n square pi square minus 1 to the power n minus 1 sine n pi x over l over n pi over l, because this is the derivative of cos n pi x over l, right? And we put the negative sign outside, right? And then e to the power, same thing. So when we'll apply 0 at x is equals to 0, so sine 0 will be equals to 0, right? So this whole function will be equals to 0, and we will only left with ux is equals to a, because sine is in the product with all this stuff. So this will be 0, so ux is equals to a. And again, for x is equals to L, same thing, we will get sine and pi in the summation, and sine and pi is equals to 0. So again, we will get ux is equals to a. So we satisfied both the boundary conditions. Now we will satisfy the initial condition. So we are giving ux is comma 0 is equals to ax plus al over 2 plus this summation. And at t is equals to 0, here it will be e to the power 0, which is equals to 1, right? So we will left with only ax plus al over 2 plus summation 2al over n square pi square negative 1 to the power n minus 1 cosine n pi x over l. And we know that this is actually equals to ax, because this is the Fourier cosine series of ax. So we can replace ax in place of this, and we see that ux comma 0 is equals to ax plus ax, which is equals to 2ax. So this conditions is also satisfied, because f of x is equals to 2ax. And now the solution, note the solution also satisfies the equation, right? The solution must satisfy this equation. So for that, you can first of all differentiate with respect to t. You can find ut, and then you can find uxx, and you will see that this is equals to 0, right? So this will be equals to 0. So in this manner, we can solve the Neumann boundary conditions, homogeneous, non-homogeneous, and hope you guys understood this lesson. And in the upcoming lessons, we will talk about the mixed boundary conditions, right? That is the mixture of Dirichlet and Neumann. Then after that, we'll talk about non-homogeneous heat equation, right? So this is all for the time being. Thanks for watching the lecture.